In this chapter, we'll look at exponential functions and log functions. Exponential functions are functions that have the variable in the exponent position. So an exponential function with base b would look like y equals a times b to the x. Okay. This b is the base of the exponent function because the variable x was in the exponent spot. We could also write this as f of x equals a times b to the x because again f of x is the same thing as y. So here's an exponential function. It models the average amount spent in dollars at a shopping mall after X hours. So the question says, what's the average amount spent to the nearest dollars after 3 hours? So the 3 hours, it tells us here that X is the hours. So this is saying that X is equal to 3. So we have 42, or Y equals 42.2 times 1.56 to the third power. You can type that in your calculator just exactly like you see it. 42.2 times 1.56 to the power of 3. And we get 160.2087, and it keeps going. But then it says here to the nearest dollar. So we want to look at this. The number after the decimal tells us to leave it as $160. So again, this is just an example of an exponential function. The graph crosses the y-axis at a, whatever that a is. If x is positive, then the graph goes like this. If b is 1, then like we said, wherever it crosses is a, and the graph would go up like that. There's also a horizontal asymptote here on the y-axis. So the graph would come along close to that and then go up through that A, and that's if b is greater than 1. So remember that the function model is a times b to the x. It's increasing. This is called exponential growth. So if b is less than 1, this number right here is less than 1, then the graph goes down from left to right like that. It still crosses the y-axis at a. There's still a horizontal asymptote on the x-axis. But because its b is less than 1, it's called decreasing or exponential decay. For both of these, the domain is negative infinity to positive infinity. The range is 0 to infinity. It's all above the x-axis, and we can't include 0 because that's where the horizontal asymptote is. Again, the horizontal asymptote is y equals 0. If x is negative, then the graph switches. So by that we mean that these two would trade places. If b was positive, then the graph would go down. If b is negative, the graph would go up. If x is negative. That doesn't happen very often, so we're not going to worry about it. So this says to graph it. So first of all, let's pay attention to the fact that the 3 is b here. We don't have an a listed, so we have to recognize that a is 1. And that's our y-intercept. We're going to have a horizontal asymptote on the y-axis, and you should always draw the horizontal asymptote as part of the graph. This b is greater than 1, so that tells us that the graph is going to go up through that point. So here we can see a is 2, so it's going to cross at 2. B is 1/3. So that tells us that B is less than 1. So the graph is going to go down through that point. So let's get our horizontal asymptote on there. And then the graph is going to go down through that. Again, that asymptote is like a floor. That graph can't cross that any place. The shape of these graphs is determined by the function, and that's how that's the shape that we are going to move left or right, or up or down. If it's inside this exponent, it's like we did earlier with being inside the parentheses. If it's added, it's opposite from what you feel like. If it's added, it's moved left, and if it's subtracted, it's moved right. If it's outside the exponent, it's like it was outside before. If it's added, it moves up. If it's subtracted, it moves down. So here, first of all, if we deal with the part that doesn't have an x, or pretend like this exponent is just an x first. It doesn't have a 1, it doesn't have an a there, but so we know a is 1. This 3 is b, and that's greater than 1, so we know it's going to go up. So we'd have a horizontal asymptote right here, and we'd have a graph that goes up like that. But now that x minus 1 is inside. So that minus 1 tells it we're going to move, tells us that we'll move it right 1. Inside is left and right, and it's backwards from what you feel like. So this spot that was right here is going to get moved to here. A horizontal line, when you move it right and left, stays there. So then this graph is going to go up through here. So that point that we used was 1, 1 because we moved it from 0, 1. Okay, so again, let's deal with it without the plus 1 piece for a second. Again, there's no a listed there, so we have to put a 1 there. A is 1, and that tells us it crosses at 1. B is 2. So that tells us, because that's greater than 1, that it's going to go up from left to right. Here's our dashed line, horizontal asymptote, and the graph would go like that. But this plus 1 is on the outside, so it tells us that we're going to move the graph up 1. So it's going to go up to here. And a horizontal line, if you move it up 1, also gets moved up. So the asymptote gets moved up to there. And then the graph goes up like that. So it has a new floor. That floor has been moved up 1, so it can't drop below that y equals 1 line. E is a number. It's a number like pi. It's called irrational. That's because it's a decimal that never ends and never repeats. And E is named E after a mathematician called Leonard Euler. You don't have to know that, but this is how you spell his name, but you say it Euler. And he is the one that kind of figured out there's this number that appears a lot in nature, in equations that model things that happen in nature. So it's called the natural number because of the nature connection, and it's E because of Euler finding it. So here's an example. It says that this models the gray wolf population in the western Great Lakes X years after 1978. If the trend continues as predicted, project the gray wolf's population in the recovery area in 2012. Okay, so first of all, we have to figure out how many years after 1978 is 2012. So we subtract first. And we get 34 years. So that's telling us that x is going to equal 34 in our problem. And it tells us right there with x years. So we'd have f of x, or y, equals 1066e to the 0.042 times 34. And if we have more than one thing in the exponent, we need to put parentheses around it. So you can type that into your calculator. You have an E button. You probably will have to do a second before you type it, and it's probably above the LN button. You'll see that it will put the power symbol on your screen, or it will pop up to the exponent spot ready for you to type your exponent. So you type in parentheses 0.042 times 34, close your parentheses. Those parentheses tell the calculator that all of that is in the exponent spot, and then just hit enter. So you should get 1066 times e to the power of 0.042 times 34. And you should get something like 4445.59, and it keeps going. We're talking about a wolf population, so it doesn't make sense to have part of a wolf. So we would round that to be 4446. And again, that's because the number after the decimal tells me to go up. Okay, compound interest formula. So this is used in money, and most money is compounded at a certain rate, and that is particularly true if you have it, whether you're borrowing money or saving money. So that's true with credit cards, it's true with loans, it's true with savings accounts that bear interest. They usually follow some version of this formula. Okay, so it's A equals P parenthesis 1 plus R over N parenthesis to the power of N times T. And the exponent should be in parentheses. A is the ending amount. P is the principal. And the principal is the beginning amount. R is the rate, and you have to change that to a decimal. And you do that by dividing by 100. N, it's here and in the exponent, is the number of times it's compounded per year. And T is a number of years. Be careful, it has to be years. There's another formula for compounded continuously, and it has an E in it. All the other letters mean exactly the same thing. A equals P times E to the RT power. So A is the ending amount, P is the principal or the beginning amount, R is the rate in decimal form, and T is the number of years. So let's look at this problem, this example. It says a sum of $10,000 is invested at an annual rate of 8%. Find the balance in the account after 5 years, compounded quarterly compounding. So that means we're using the first formula. And quarterly compounding means that it's compounded 4 times per year, just like 4 quarters in a dollar. So it's telling us N is 4. The rate is right here. Rate is 8%, so we would take 8 divided by 100, and we get 0.08. So that's what we're going to put in for R. And they tell us 5 years is T, so So that's 5 years is our time, so t is equal to 5. We're starting with $10,000, so that's our principal or our beginning amount. And we're trying to figure out how much is the ending amount, the balance, so we don't know A. So we have 10,000 times 1 plus my rate is 0.08 over the number of times it's compounded per year. So we have 4. And that n is still 4 times the time is 5. So that's our formula. We can type that in just like we see it all at once. We'll type in 10,000 parenthesis 1 plus 0.08 divided by 4 parenthesis to the power of 4 times 5. Make sure that that exponent is in parentheses here as well. And your calculator will figure it all at once. And then you get 14859.47396. But it's money, so we went to the nearest cent. So the 3 after the 7 tells us to leave that a 7. So we'd have 1,400, or sorry, let me get that comma in the right spot. $14,859.47. And this one says compounded continuous compounding, so that's the cue to use the other formula. Anytime you see that word continuous, it means we want to use the formula that has the E in it. So again, my P is, my beginning amount is still 10,000. My rate is still that 8%, but we divide by 100 to give us 0.08. My time is still 5 years. Let me use a different color for that since I already used green. Okay, and we're still trying to find the ending amount, so we're still trying to find A. So I have $10,000 times E to the power of 0.08 times 5. And again, you can type that in your calculator just like you see it. Type in 10,000, and then that E button, remember that's a second, and it's above the LN, and it's going to go ahead and put your exponent position there. Parenthesis 0.08 times 5, parenthesis, enter. And that gives us 14918. And then it says 24.2, and then it's 4, 6. So the 6 makes the 4 become a 5 to round it to the nearest cent. Remember, cent means that you have 2 numbers after that decimal. We have to look at the third number in order to tell where to round. So that's our first look at exponential functions.